Now we begin the second lesson. That was about linear motion. So what is a linear motion? First, we can introduce the displacement, velocity, and acceleration. For this part, suppose we have a line, we can consider a one-dimensional case, that an object is moving along this line. Suppose this is origin point O, and this is x t. That x equals xt represent this particle move the position x has a relationship with the time t, and which can be represented by this equation. And this is also called linear lines motion equation. So when this, at first it was an x point, and it's traveled delta x in a delta t time. So that now the object in t plus delta t is at the place x t plus delta t. So that this delta x equals x t plus delta t minus x over t is called the displacement in the interval of this delta t. When delta x is positive, it represents that it's moving towards the positive direction. When x is negative, it represents the negative direction for the x-axis. So, in an infinite small time interval, the displacement is also an infinite small displacement. We can call that a dx. And what we refer to as like a countable limited delta t time interval. It's delta x, displacement delta x. Delta x is equal to sigma dx t plus delta t, because it's add up each small interval between this delta t time, and each small time interval it got an infinitely small displacement. We add them up, it's the total displacement, and it is also equal to integral t plus delta t the dx. We have another kinematic quantity which named the distance. We can represent it with s. Distance means what the object moved in delta t time, the total length it moved. So that s is equal to sigma t plus delta t, the absolute value of dx. Because if it moves back and forth to the origin point, we can easily see that its displacement is zero because it has no relative movement. But its distance is not zero, as it moved and moved back, right? We can write this as integral t plus delta t times the absolute value of dx. So we can always see that the distance must be larger or equal to the delta x, the absolute value of delta x. And so we can thus introduce the average speed. The average speed is defined as delta x divided by delta t. That it means in the total effect, the particle move in this direction, the average speed, whether it's fast or slow, is represented by this average speed v. So, the average speed v we can easily see is a vector because it represents its direction. The speed has a direction because it's associated with displacement. So when the average speed is positive, it represents that the particle is moving towards the positive of the x races, and it was negative, it was moving backwards. So if we take a very, very small, infinite small time integral where delta t goes to 0, that in this very infinitely small time interval, the average speed in this delta t time will approach an instant speed, which we call just v. And this instant speed is dx dt, which means in an infinite small displacement divided by an infinite small time. So mathematically, the speed is an one-time derivative of the position to time. In an SI unit, the unit of v is meter per second. The absolute value of the velocity is called speed. So, but sometimes it's also just written as v. But you must see that when you see a v, whether it's like represent the velocity, which is a vector, or the speed, which is a scalar. You must see from the passage. In any case, speed will change with time. So that the same way we introduce with speed, we can introduce an average velocity and acceleration. That means changing velocity divided by changing time. Just as we introduce changing displacement divided by changing time. So the changing in velocity is also, we can refer velocity at t plus delta t time minus velocity at time t. So when this interval goes very, very small, we can introduce the instant acceleration. We can just write a as dv dt, which is a one-time derivative of the velocity. It is also a vector. And we can also substitute the equation 1 is d squared x dt squared. That means it's the second derivative of the position x, the displacement. You can always introduce like the third derivative or the fourth derivative or something like that. But all these, like above 2, is rarely used. So generally, we don't do that. Because after the kinematics, we will introduce the particle dynamics, which the Newton law only have something to do with the acceleration. So our introduction will stop to the acceleration. We know the derivative of the position is velocity. The derivative of velocity is acceleration. Thus, we can do the inverse, such as the integral of velocity will give us the position. Integral of the acceleration will give us the velocity. Like we can write at v0 to vt dv equals integral t0 to t at dot dt. So that means vt equals v0 plus t0 to t at dot dt. And this part is exactly changing v. The same, we can write xt equals x0 plus integral from t0 to t vt dot dt. And all these, the velocity, acceleration, changing with time, can use the graph to represent. For example, if we have like a small sphere and is thrown upwards with 9.8 meter per second, the initial velocity, we can see the velocity diagram. It's like going downwards like this. And the acceleration diagram is like this. So that the velocity v(t), if we take another case, was like it's doing simple harmonic motion. It would look like that. And this is the V maximum. This is the minus V maximum, V minimum. Then thus the acceleration, v(t) gram, we can see is going like this. And this is the maximum of the acceleration, 2 over t.